This video goes through angles in circles and our learning goals to prove and apply angle properties of circles. First, some definitions. Firstly, a chord, a line segment with endpoints on the circle. So in the diagram here, AB is a chord. Okay, if you have a chord that passes through the center of the circle, so CD for example, it would be called the diameter. Segments, every chord divides the interior of a circle into two regions called segments. So if we look at chord AB, we have two segments. We have this shaded segment on this side, and then we have this large segment on the left-hand side. Now, the smaller segment is called the minor segment, and the larger segment is called the major segment. Moving on, let's go to arcs. Now, any 2 points in a circle divide the circle into arcs. Now, I've got a diagram here on the left-hand side. So you've got 2 points, A and B. So we have an arc being formed by A and B. So our arc, I'll highlight the arc rather than the segment. Our arc is that point there. So ACB is my arc. That's my minor arc. I also have ADB, which would be my major arc. Now, with those points that I do have another two arcs. I could have DAC, and I also have CBD. So two other arcs. Those ones would be called semicircular arcs because they go around us the semicircle. Finally, sectors. Thinking about our arc. So here's my ACB arc. It creates a sector. So we have a sector here. That would be my minor sector. We also have the sector on the other side, which is my major sector. Now let's start looking at our theorems. Now firstly, a theorem is a mathematical statement that can be shown to be true, and a proof is a step-by-step argument that demonstrates the truth of the mathematical theorem. Okay, so we know with mathematical theorems that things are true, but we go and we prove them to be true. So we have three circle theorems that we're starting with. The first one is that the angle at the center of a circle is always twice the angle at the circumference subtended by the same arc. So firstly, our arc is there. So there's my arc, and going to the center of the circle, I'll go different color. Okay, so we have to the center of the circle, and then we have to the outside of the circle. So that means that's what it means by subtended by the same arc. Okay, so if that happens, the angle in the middle here is twice the angle on the outside. Looking at a different way of drawing that, so it looks a bit different. Again, here's my arc, but now my arc is going more than the semicircle, so it looks a bit different. So subtended on that arc, I go to the center, I go to the outside, and then my angle in the middle is twice the angle on the outside. Now, an extension of that is circle theorem 2, which if we have our arc, that's a semicircular arc, okay, so it goes around the semicircle, then when we draw, I'll keep it the same colors, so I'll draw that in green. So we have a semicircular arc here. Then just like before, we go from the semicircular arc through the middle, out to the outside. Now because this chord that I've just created is the diameter, it makes a 180-degree angle because it's a straight line. So this angle here at the circumference is half that, so it has to be 90 degrees, so it's a right angle. Okay, finally, our semicircular theorem, I like our circle theorem 3. Circle theorem 3, I like to call the bow tie. Angles in the same segment, subtended by the same arc at the circumference, are equal. Okay, so we have our arc here. Okay, so if we draw our bow tie, there's our bow tie. So that means that this angle is equal to that angle. And similarly, we also have an arc on the other side, so that angle has to equal that angle. So just note that that's based on we have the two arcs on either side. Okay. Okay, now let's look at this one. A, B, C are 3 points on the circumference of a circle with center O. Prove that AOB, so this angle here, is equal to 2 lots of ACB, which is the angle here. Okay. In order to do this one, we can't do much with what we've got, but if we construct a line through through OC, and we call this D, I now have created 2 triangles. Okay, so our first step is to construct line CD through O. Okay, now if you look at the 2 triangles I've just created, O is the center of my circle, so that means that's the radius, and that's the radius. So all of those are equal in length. So OC equals OA equals OB because they're the radius, or radii for a plural. Okay, so that means I've just created 2 isosceles triangles. So triangle AOC and triangle BOC are isosceles. So to make this easier for you to understand, because they're isosceles, we know that this angle here has to equal that angle there. So let's let them equal x. So angle OCA has to equal angle OAC, and we're going to let them equal x, and they're base angles of isosceles triangle. Okay, similarly, let's let these base angles be y. So angle OCB equals angle OBC, and we're going to let them equal y, and that's the same reason. Okay, so if we look at my triangle AOC, that means this angle here has to be 180 minus 2 lots of x because of a angle sum of a triangle, and then this angle here has to be 180 minus 2y, again because angle sum of a triangle. So angle AOC has to equal 180 minus 2x, and angle BOC has to equal 180 minus 2y, and I'm going to write the same rule, angle sum of triangle. Okay, so that means this angle here that's a straight line. Okay, so if I use a highlighter for you to see that, we're dealing with this straight line here. So that means that angle there has to equal 180 minus the 180 minus 2x, because I have to add up to 180 degrees. Okay, similarly, the same for the other angle on the other side. So this angle here has to equal 180 minus 180 minus 2y. Again, because it's a straight line. So let me write that down. So angle AOD equals 180 minus 180 minus 2x, which is simply 2x. And angle DOB has to equal 180 minus 180 minus 2y, which is 2y. And the reason for that is they're straight lines. So angles add to 180 degrees. Okay, so that means that angle AOB has to equal 2x plus 2y, or bring the 2 out, 2 lots of x plus y. Angle ACB is equal to x plus y. So I have just proven, therefore, angle AOB equals 2 lots of angle ACB. Okay, now let's look at this one. CD is a diameter of a circle with center O. E is a point on the circumference. Prove that angle CED is right angle. So we're proving our circle theorem 2. We do it because it's a follow-on from circle theorem 1. We actually prove this in exactly the same way. So we construct that line and label that D, and we go through exactly the same process as what I just did. So from there, we know that they're all radiuses, which means that now I have 2 isosceles triangles. So x, x, y, y. Okay, I'm not making any assumptions that they're identical. I'm just going x, x, y, y. So that means this angle in here has to be 180 minus 2x. That angle in there has to be 180 minus 2y. Following on from that, this angle here has to be 180 minus 180 minus 2y, which is 2y. Note you could use exterior angle of a triangle to do this as well, which is basically just wait one sec. This angle here is equal to the sum of those two angles. So if you knew your exterior angle of a triangle rule, you could just go that, which would be a lot quicker. But I'm assuming that you guys aren't remembering that, but you could. Okay, so similarly, that angle there is going to be 180 minus 180 minus 2x, which is 2x. Again, I could have used the exterior angle of a triangle, which is that angle plus that angle has to equal that angle there. Okay, which it does. A lot quicker, but I suppose I've proven the exterior angle of a triangle at the same time. I have now done what I needed to do, but I need to write it all out. I'm going to do that. I'm going to pause the video, write it all out so you don't hear me doing it, and then get to the final step. Okay, firstly, when I was writing out the proof, I realized I already had a D, so I changed the D that I labeled for my construction of my line to F. So my first step was construct EF through O. And then I go through all the steps that I've already explained. The only bit that I got up to was down the bottom, which is that 2x plus 2y is 180 degrees because you have this straight line through DC. So that's a diameter. So that means 2 lots of x plus y has to be 180 degrees, or x plus y is 90 degrees, which is your angle DEC. Okay, in this one we have to prove our bow tie theorem, and it wants us to prove that angle ACB, so this angle here, equals angle ADB, so that angle there. Now, how to do that is to construct a couple of lines as well. So what I'm going to construct, I've got this center. If I draw the center to B and the center to A, I now have my Theorem 1. Okay, so what I mean by that is if I let this angle here be A, this has to be 2A because they're sitting on the same arc. Okay, similarly, this angle out here has to also be A because it's sitting on the same arc. So there. And that's basically a proof because you've just proven the angles at the edge are the same. So our first step was draw OB and OA. Therefore, angle ACB equals a half angle AOC, and angle AOB equals a half of angle AOC. And the reason for that is angle at the center is twice the angle at circumference. I should put subtended by the same arc, but anyway. And our code for that, if we want to do, oops, that's a bit dodgy. Our code for that is that one. Okay, so therefore, angle OCB has to equal angle ADB. Okay, I'm just thinking I could have, yeah, that's fine. We'll leave it at that. So let's look at just applying these theorems. So here, determine the value of the polynomials in these circles, giving reasons for your answers. The first one, angle BOC would equal 2 lots of angle BAC, and I can put the code for that. Okay, angle at the center is twice the angle at the circumference, so that means 126 has to equal 2 lots of A. So A would be 126 divided by 2, which is 63 degrees. In the next one, there's my center, my O. So that means angle ABC has to equal a half angle AOC, which has to be 90 degrees. Okay, so I know that that's 90 degrees. So that means that my angle BAC has to equal 180 minus 90 minus 70, and that's because it's an angle sum of a triangle. Okay, so A has to equal 180 minus 90 minus 70, which is 20 degrees. Next one's my bow tie. A has to equal 30 degrees. Happy for you to write bow tie if you want, or you could write the code, which is that one there. Final one, I have an isosceles triangle. The first thing I ever do in these is draw in radiuses. It's a good idea to start with. Angle AOB has to equal 2 lots of angle ACB. So that means it equals 2 lots of A. And the reason is the angle at the center is twice the angle at circumference. I'm going to write down that AO equals BO because they're radiuses. That means, therefore, triangle AOB is isosceles. And angle OAB has to equal 25 degrees because it's base angle of isosceles. Triangle. So now if I put in all that information, that's 25, that's 2A there. So that means 2A plus 25 has to equal 180 degrees because of angle sum of a triangle. So you've got 2A plus 50 equals 180, 2A equals 130, so A has to equal 65 degrees. Last one, BC is the diameter of a circle with center O. E and F are points on the circumference of the circle such that OF is parallel to CE. If angle OCE is 35 degrees, find the angle of OFE. I'm going to highlight what I need to find, OFE. So I'm trying to find that angle there. Or put it with a red circle, don't mind, but just so you have a focus on what you need to find. Giving reasons for your answer. First thing, as I said I always do, I put in where my radiuses are. The other thing I'm looking at is the fact that I have parallel lines, so I'm going to be thinking about that. But with my radiuses, I know that this has to be 35 degrees because it's base angle of an isosceles triangle. So that means that angle there has to be 180 minus 35 minus 35, or 180 minus 70, so that's 110 degrees, angle sum of a triangle. Okay, using our angle properties, we have a Z here, so that means this angle in there has to be 35 degrees. So that means these two angles are the base angles of an isosceles triangle. Okay, so they have to be equal to 180 minus my 35 divided by 2. Okay, so that's the proof in a nutshell. I'm going to pause, write it all out, and then go through it. Okay, so pause so you can read through that, but it's basically what I went through. Go through the radiuses, identify my isosceles triangle, stated that my angle CEO was 35 degrees because it's base angle isosceles triangle. From that, worked out COE, which is 180 minus the 35 minus 35 because it's an angle sum of a triangle, so that's 110. From there, angle CEO equals angle EOF, which is 35 degrees because they're alternate angles, or my Z rule. So angle OEF has to equal angle OFE because they're base angles of an isosceles triangle. I should write triangle there. Therefore, angle OFE has to be 180 minus the 35 divided by 2 because it's a base angle in an isosceles triangle. So it's 72.5 degrees. And we're done.